Welcome back for another day of Math 8. Here we are with Unit 2, Lesson 2. And I'm going to introduce you to this circular grid. We've seen lots of grids this year, and in our lives we've seen the square grids where we just see x and y axes, vertical and horizontal lines intersecting. We've also been introduced to isometric grids this year where we see equilateral triangles that intersect each other at 60 degrees. Now we see this one as a concentric circle or circular grids. Go ahead and take a minute to answer the question, what do you notice and what do you wonder? All right, thanks for doing that. What we're doing with this today is we're going to be working with dilations from a little bit different perspective, but just remember dilation is simply a way of making a scaled copy of geometric figures, a way to make something larger or smaller depending on what our scale factor is. When we look here, a larger circle, D, so this outer circle D, is the smaller, or is a dilation, so it means it's something that grew larger, is a dilation of the smaller circle C, where P, right here at the middle, this is called our center of dilation. So we have a dilation where circle D actually was grown from the circle C, and then center P is our center of dilation. So everything grows and shrinks from that center point. We're supposed to draw 4 points on the smaller circle, not inside the circle, and label them E, F, G, and H. And it really doesn't matter where we put those, but we just go ahead and put them on there. So let's go ahead and put one right here. We'll call this one E. We'll put another one over here. We'll call this one F. And then G right here. And we'll go ahead and space H out. Let's go ahead and put H right here. Again, you can put them anywhere you want. It doesn't really matter. Now we're supposed to draw some rays from point P through each of those 4 points. We're going to go ahead and start out right here. With E, we'll start right here at center of dilation, and we're going to continue out like this. I'm going to go out far enough so I can see it go outside of the circle. We'll continue to do the same thing for each of these points. And I'm drawing our ray from the center of dilation all the way out. And then finally H. And the next step is we're going to label the points where the rays meet the larger circle as E prime, F prime, G prime, and H prime. So we'll start out with here with E. We come out to the next circle. I've highlighted these just so you can see them a little bit better, and this is E prime. We follow F out here to F prime. We follow G out here to the outer circle at G prime. And then we'll follow H to the same thing, making that H prime. Okay, there you go. Number 4, complete the table in the row labeled S. Oops. Write the distance between P and the point on the smaller circle in the grid units. In the row labeled L, write the distance between P and the corresponding point on the larger circle. So we have the smaller circle, we have the larger circle. First thing, from P to E is just 2 units. So when we count this, we go from here 1, 2. We see that F is 1, 2, G is 2, H is 2. So these are all 2. When we talk about L, in the row labeled L, write the distance between P and the corresponding point on the larger circle. We're going to go out a little bit further. We know here's 2, 3, 4, 5, 6. We see the relationship all the way around on each of these. So we have 6, 6, 6, 6, 4 times there. The center of dilation is point P. What is the scale factor that takes the smaller circle to the larger circle? Explain your reasoning. What we saw in the last lesson is we could determine scale factor by taking the dilated image and dividing its length by the original image. So when we talk about these, we talk about how we had 6 for my dilated length and then 2 for my original, which tells me that this reduces down, or excuse me, the division is 3. So that would tell me that my scale factor is 3. And my explanation for that is we know that there's a growth rate that happens right here. So if this was 2 units long, and then that length from point P, the center of dilation, to point G grew to 6 units long, then we know that it has to be a growth rate of 3 times larger, or a scale factor of 3 times the value of 2. So when we want to find our scale factor, we simply need to look at the dilated length and divide it by the original length. Let's see a little bit more practice. Here's another figure, except this is a quadrilateral on a circular grid. We're going to take a few steps to see what happens as a consequence of dilation. First thing we're going to do is dilate each vertex of polygon ABC using P as the center of dilation and a scale factor of 2. Keep in mind that now we're using a scale factor. Scale means how much larger, and the factor means times, so how many times larger. In this case, it's 2 times larger. We're going to label the image of A as A prime, and then we're going to go ahead and continue the other vertices as B, B prime, and C. What I want to look at here is the distance for A from P to A is 1, 2, 3, 4 units. So we're going to talk about there's 4 units, and we want to go ahead and dilate that by a scale factor of 2. So we'll multiply by 2, making that a unit of 8. So we're going 4. We're just going to double that distance, 5, 6, 7, 8, and make this A prime. We'll do the same thing for B, C, and D. So right now B is 2 units away from the center of dilation, meaning that our scale factor of 2, we'll take that out to 4 units away. Here's B prime. We'll do the same thing for C is 1, 2, 3, 4, 5. Twice the distance, or scale factor of 2, is going to give us a distance of 10, 6, 7, 8, 9, 10 for C prime. And then D is 1, 2, 3 units times 2 would make our dilated length 6 units. 4, 5, 6. There's D prime. And then we're supposed to draw segments between the dilated points to create polygon A, B, C, D, or A prime, B prime, C prime, D prime. So there's that side. Please use a straight edge. I forgot to remind you at the beginning of the lesson that you should have a straight edge or a ruler. If you do not have one currently, please go ahead and pause the video and find one, or just pause the video and fold up a single piece of paper a couple times to give yourself a nice straight edge. Also, while you're pausing that video, go ahead and answer this question right now. What are some things you notice about the new polygon? All right, we're going to go ahead and choose a few more points on the sides of the original polygon and transform them using the same dilation. And what do you notice? So let's go ahead and go in here. Let's just put one, let's put one right here and right here. If we're going to use that same dilation, what we see is just a little more than 2. This looks like about 2 1/3. So 1, 2, 2 1/3. That means double that should be 4 2/3. So there's 1, 2, 3, 4, and that is approximately 2/3. You notice how we follow out that same line like the rays that we did with the other ones? What we're doing is we're being able to go ahead and measure that and see that there is a larger piece, or there are more than one ways to go ahead and dilate by using that same dilation. But the key thing is that we're going from one line and we're using the next line, the one that created out here, to be able to see the same relationship, that this length of the segment from the center of dilation to the edge is doubled. These two segments are exactly the same length. Number 5, we're supposed to dilate each vertex of polygon ABCD using point P as the center, but this time we're going to use a scale factor of 1/2. That means that original length that we had of 4, 2, 5, and 3 is now going to be cut in half. So when we look at these ones, we're going to take A is going to turn into E, B is going to turn into F, C is going to turn into G, and D is going to turn into H. So from here, we're going to go 4 times 1/2, which is equal to 2. We'll take 2 times 1/2, which is equal to 1. 5 times 1/2, which is equal to 2 1/2. And 3 times 1/2, which is equal to 1 1/2, or 2 5/10, 1 5/10. And we're going to go ahead and label these on here. So going from P to A, we saw it was 4 units. Now we're scaling back to 2 units. So we're going to call this one point E. And then we're going to go to B, which goes from 2 units to 1 unit, just half the distance out to B. This is now point F. Point G, this one might be a little trickier, but we're going to go to 2.5 units, half the distance to C, 1, 2.5. Be as close as you can on that one, but label it point G. And then H, 1 1/2, half of 3 right here. Go ahead and connect those dots as it says. We're going to go ahead and just see what happens. What does this shape look like compared to its original? As you may have noticed that the figures continue to remain in the exact same shape. It actually kind of looks like we're looking down some kind of a hole into that center, or perhaps it's coming up as some kind of a pyramid prism type of thing. But just think about that. What do you notice about this figure E, F, G, and H as compared to A, B, C, D, its original image? Hopefully what you're seeing is that the shape of the polygon didn't change at all. The angle measures are exactly the same as they were. So the angle measures are preserved, but the length of each segment is actually taking on something else. These segments right here are actually shorter than the next one. These ones are longer, but what we can look at with these ones, especially with where we drew this piece right here, we're going to see that this segment right here is actually half the length of this segment, and this segment is half the length of this segment. So if I double this segment of FG, I get BC. And if I double the length of segment BC, I get B prime, C prime. So we see that that dilation continues to have that same pattern that we discussed in the previous lesson, just based on the fact that we have a scale factor of 2 to increase in size to the blue polygon, and a scale factor of 1/2 to decrease by a scale factor of half in the red polygon. Let's look at that in one more example. Feel free to go ahead and try the Are You Ready for More on your own. Email me your results. When we look at quadrilateral and concentric circles, this one you can go ahead and do the digital interactive version at this website if you choose, or you can go ahead and follow along with me right here. We're supposed to dilate polygon EFGH using Q as the center of dilation and a scale factor of 1/3. The image of F is already shown on the diagram, and you may need to draw more rays from Q in order to find the image of other points. So let's go ahead and do this. We know that we have a ray that goes from Q and emanates out to the outer point there. So we're going to go from Q to G. The reason for this, it'll help us to put our points in the exact places that they need to be, because the dilated images need to be what's called collinear with the center of dilation. Means that they have to line up on the same line, the center of dilation, the original point, and the image of the next point. Now working with a scale factor of 1/3, we see on letter F that we actually got closer to the center of dilation. That's because our distance from Q to F is shrinking because our scale factor is less than 1. When we look at E, we see that there's a distance, an original distance of 3 units. When I multiply that by 1/3, my scale factor decreases that distance down to just 1 unit. And so we have that value here creates point E, just like we see in F, how it was 3 units long, or 3 units away. By multiplying by a scale factor of 1/3, we actually decrease that distance to just 1 unit. When we look from Q to G, so F had the same relationship. G starts out as 1, 2, 3, 4, 5, 6 units away. 1/3 of that distance will be 2 units. So that means we bring point G in here into here for G prime. Excuse me. And then H, 1, 2, 3, 4, 5, 6, 7, 8, 9 units. 1/3 of 9 is 3, so it's going to come out 1, 2, 3 units. Uh-oh, I messed up on G. I put it in the wrong spot. That one should be right here, not out there. That would have been a tragic mistake, because we would actually see a very big difference in the two shapes. And we can't change the shape, but all we can change is the size. So we go ahead and connect these points. And what we should see as we do this as we connect these points is we should see that under this dilation, I get the exact same figure, but on a much smaller scale. Notice that all of the corresponding sides, the corresponding segments, are parallel to their original. If I would have done that right here, notice that this segment G prime H prime is not parallel with GH. And that would be a mistake because under dilation, the corresponding sides have to be parallel to their original. Otherwise, I didn't do my dilation correctly. So that'd be a good way to double check. If you draw your picture and it doesn't look like the bigger shape, then there's probably something wrong. You probably put your figure in the wrong spot. So that's where that would look. You could do this with several other pieces, growing or shrinking. Either way, we understand that that scale factor is something that's just going to be growing and shrinking the image to either make that image larger, as into the blue, or smaller down to the red, and in this case, smaller into the blue one. Everything relating back to the center of dilation. Wrapping things up, a circular grid like this one can be helpful for performing dilations. This is something that's pretty new. I think it's pretty cool. This is my first time using a circular grid, and I really like it for dilations. In this situation, the radius of the smallest circle right inside here is just 1 unit, and the radius of each successive unit is 1 more than the previous one, so we see that that successive rate out here just continues to grow and build on itself. Keep in mind that all dilations, as we perform dilations, we need a center of rotation, we need to have a scale factor, and we need to have a point to dilate. In the picture right here, we see P is the center of dilation, and with a scale factor of 2, we bump out from 3 units to 6 units. Notice that each point stays on the same ray from P, but its distance from P doubles. Since the circles on the grid are the same distance apart, segment PA prime has twice the length of the segment PA. Now, if you remember in a previous lesson, I said you notice that the size of the figure doesn't necessarily match the scale factor. The reason for that is because when we're talking about scaling or talking about dilation, we're talking about only the distance between 2 points changing. In this case, if we're talking about from P to A, it's 3 units long. The distance from P to A prime under dilation of a scale factor of 2 would be 6 units long. The cool thing is that the side lengths of the figure, as a consequence, will also follow that same pattern, where the length of AC is going to double its length to A prime C prime. So A prime C prime is twice as long as AC as a result of the dilation. That's it for the lesson. Let's move on into the homework. Maybe. Okay, there it is. Question 1, when it says here are circles C and D, point O is the center of dilation, and the dilation takes circle C to circle D, meaning that the dilation is going to grow from circle C, from the blue one to the red one. So let's see what happens here. It says a point P is plotted on circle C. So we'll go ahead and just put a point out here. And a ray is drawn from O through P. Oh my goodness, let's see if I can do any kind of justice here. Oh, forgive me. I know it's not a straight line. So you're like, that's not a ray, but we're going to pretend that it is. It says, where is point P plotted when the dilation is applied? Well, if we follow this ray straight out here, this is point P, or excuse me, yeah, point P. And then when I dilate further, point P is just right there on that same ray, just out on the next outer circle. So when we're talking about these pieces, it says, where is point P plotted when the dilation is applied? Try and keep this picture in mind. I have to close this so I can do this option. Is it anywhere on circle C? No, it wasn't anywhere, because the point was somewhere right around here, and then it went out, straight out further. And we don't really see, it can't just be anywhere on circle D. It can't be the intersection of the line with circle C, but instead it's the intersection of the ray and circle D. So remember that ray that emanated from here all the way out, we had that straight line. Go ahead and do part B as well on your own. Number 2, you'll have an opportunity to go ahead and practice some dilation. So here's triangle ABC in its original form. Here is a series of dilations where you have triangle number 1 is this little tiny one on the inside. Triangle number 2 is the outward one here. So we have the original ABC is right here on the inside, or excuse me, is in the middle of the other two. Read carefully as you work on this. Which triangle shows triangle ABC dilated using P as the center of dilation by a scale factor of 2? Quick tip here. Anytime we see a scale factor that is greater than 1, there must be growth because we see it doubling in size in this case, or doubling in the length of segment. Anytime we see a scale factor that is less than 1, so meaning between 0 and 1, as a fractional value that's between 0 and 1, we know that the dilation must be shrinking in size. So pay close attention to that as you answer these two questions, and then use that as you answer other questions. Question number 3, a little bit of review going back to rigid transformation. Question number 4, a little more review going back to some work with the triangles and the interior angle sum of triangles, straight angles, so on and so forth. Go ahead and take care of your homework. Thanks for hanging in there for the lesson. Make sure you never give up. Have a great day.